In this video, we're looking at vectors, specifying, adding, and subtracting them using a variety of methods. Specifically, we want to do this so that we can describe both 2- and 3-dimensional motion. Up to this point, we've really been looking at 1 dimension, and we'll still look at 1 dimension at a time, but we want to be able to do more than that. We want to be able to talk about the magnitude of a vector and its direction. We're going to look at graphical methods using magnitude and angle to talk about a vector, using components, and using unit vectors. Lots of different ways. Graphically, you can literally draw the vector. The length of it represents its magnitude in whatever scale you're dealing with, and the arrowhead gives us a direction. With an angle and a magnitude, vector P here is 2 meters long, and it is at an angle of positive 30 degrees. So we're always going to measure our angles counterclockwise from the positive x-axis. This is sort of the way you think about defining the unit circle. You can also use north of east, east to north of west, that kind of thing, if you want. And you can also measure up from the negative x-axis, which is sometimes more convenient. Like that q vector could be, instead of 150 degrees, it could be 30 degrees above the negative x. So a couple different ways to think about that. We can also do this with components. Whenever you have a vector, say this vector A that is 5 meters long, that has an x component or a horizontal component of 3 meters and a y component of 4 meters. This, of course, being my favorite right triangle, the 3, 4, 5 right triangle. And these components are always at right angles to each other. So they give us very nice ways of defining it. We can also do this with velocity, 30 meters per second at some angle. We have the x and the y components. To find the components, you're really just doing some right angle trig, right? If you have a vector that is 2 meters long at an angle of 30 degrees, the x and y components come from a cosine 30 and a sine 30 respectively. And you can write them in an ordered pair or a few different ways. It's important to pay attention to signs, right? If the x component is switched to be negative, it completely changes the direction of the vector. These vectors are both the same magnitude and have the same y component, but different x components. Right, and you can see that here. We have x, y components that if they're going to be both positive, both negative, one positive, one negative, what they look like. We also can use the unit vector ijk, right? I is 1 unit long in the x direction, positive x direction. J is 1 unit long in the positive y direction, and k is 1 unit long in the positive z direction. So a vector could be given, positive 1.7 meters I hat, positive 1.0 meters j hat. That's in the xy plane. To add and subtract vectors, we can do this graphically or analytically. Graphically, you're just to scale laying them out, A, then B. Think of it like following a treasure map. Go follow A, then follow B. C is the vector that you could have taken to get to that point if you knew where to go. So this is called the tip-to-tail method. A couple of important things. Vector addition is commutative, meaning you can go A to B or B to A, but these do not add up. The magnitudes do not sum. Right? That's an important distinction. If we add vectors graphically, we can also use a parallelogram, and the resultant is the diagonal. This is another method. If we're doing graphical subtraction, subtracting a vector is basically adding its negative. And a negative of a vector, as you can see with vector B here, is just putting the arrow on the other end of the vector. So which of these is the correct diagram of adding A or subtracting A minus B? Well, if B is due north, then negative B is due south. So the best answer here is C. If vector addition of commutative, is subtraction also commutative? It turns out that it is not, right? If you subtract a vector, A from B, you will get a different answer than B from A, right? So you just have to watch out for that one. If you want to add and subtract them analytically, it's much easier to use collinear vectors, right? Two vectors in the x direction, either they're positive or negative, just add them together and you'll get the answer. Doesn't matter. That works very nicely. But if vectors are, at arbitrary angles, right, then you have to use components. Vector A, 3 meters, B, 4 meters in the x and y direction. We can use Pythagorean theorem to find the magnitude, the tangent to find the angle. If they're randomly oriented, one method you can do this is to find their x and y components first, add the x components, add the y components, then put them back together as a new right triangle. So this is our steps. We find the x, y, and z components of each vector, add all the x's, add all the y's, add all the z's, keep track of your signs, is it positive or negative, and then put them all together, right? So here's our example. My car drives 50 kilometers east, then 30 kilometers north, then 100 kilometers south of east. We have our A, our B, and our C in components, add all the x's, add all the y's, put them together, right? Then we can get the final vector by using Pythagorean theorem and the inverse tangent. You can also do this if they're already in unit vector form. They've already been written in components. You can just directly add them that way. Last conceptual question here. If two vectors lie in the xy plane, what are the signs of the x and y components? You can pause and take a look. But d1 plus d2 is going to be negative x, positive y. d1 minus d2 will be two negative signs, x and y. And d2 minus d1 will give us both positive. All right, so there's plenty of vector practice on pages 37 and 38, optional. Do as much or as little as you need.